In example 3, we're going to look at 2 more homomorphisms to learn a little bit more about how homomorphisms work and to lead us towards being able to generalize some properties of homomorphisms, just as we did with isomorphisms. So in part A, we're looking at the homomorphism phi from Z6 to Z6, defined by phi of x equal to x mod 6. We see the Cayley table right here, but you can also use a formula to figure out what phi of 0, 1, 2, 3, 4, and 5 are. Okay, so what's phi of 0? Well, that's 2 times 0 mod 6, that's 0. Phi of 1 is 2 times 1 mod 6, that's 2. Phi of 2, that's 2 times 2, that's 4, mod 6 is 4. Phi of 3 is 2 times 3, that's 6, mod 6 is 0. That's a 0. Phi of 4, similarly, is going to be 2. Phi of 5 is 4. Okay, so here we are. What's the kernel of this map? So the kernel, which we are just going to denote with the letter K in our case, is everything that maps to 0. And there are 2 things, 0 and 3. So there's our kernel, 0, 3. And then they are also asking us to list the left cosets of the kernel. So here we are, the kernel is a subgroup of Z6. So this is a subgroup of Z6. And let's look at the left cosets. Well, there's the kernel itself that we're just going to call K. And then we have 1 plus K. And that has elements 1 and 4. K itself, of course, was 0 and 3. And then we have 2 plus K. And that is 2, 5. And that's it. So we got 0, 1, 2, 3, 4, 5, all accounted for. So these are the left cosets of the kernel of phi, which were just called K. Now, what do you notice right here? Let's draw a little diagram to visualize what's going on here. So we started out with these 6, and we have 0, 3, 1 and 4, and 2 and 5 mapping to the same thing. So that's why I wrote them in this order. So 0 and 2, that's our kernel. Those map to the element 0. So the whole thing, phi was described as just, well, let me